Hi everyone. I've long been interested in cryptocurrency and specifically Bitcoin, which has been around for almost 15 years now. So I'm sure there are others like me who also find the concept, intriguing as a technology. I've recently been wanting to learn more about Bitcoin and how it actually works. So I've taken to some books, reading the code, watching videos, and ultimately I've decided that I think the best way to learn something like this is to build it from scratch. So this will be the first video in a series of building Bitcoin from scratch in Python. We'll take it piece by piece, hopefully in a way that is much simplified from the actual Bitcoin core code, so that it's approachable for someone who has a rudimentary understanding of Python, but maybe not anything about cryptocurrencies or Bitcoin. So obviously there are some sacrifices we make with that. It won't be, as performant, secure, things like that. We won't be dealing with all the networking that goes on. Obviously, Bitcoin core developers have been working on Bitcoin since the beginning, so it would be probably not useful to go through all of the details and rebuild it actually from scratch. But this will be more of a theoretical exploration and implementation of Bitcoin, just to see if we can get kind of the core components and principles working. So with that, let's get started. I think the first piece that I want to dive into today is how do elliptic curves work and what is their importance in Bitcoin. So the first thing we'll do is I have Desmos up here, which is just a visual graphing calculator, where we will plot an elliptic curve, specifically the one that Bitcoin uses. Find the formula for this. This is what it's called. I'm not sure exactly how to pronounce this, but the equation is y squared equals x cubed plus 7. Actually, there is, I think, another general term of the formula that is 0 here, so maybe I'll get that as well. Okay, so here is the formula that we'll be starting with in Desmos here. So y squared equals x cubed plus ax plus b. Okay, so this is our general form of an elliptic curve, and the specific implementation of Bitcoin is where a equals 0, that's why this middle term is missing, and where b equals 7. So we will pop those in. A equals 0, and b equals 7. Okay, so this here is what the Bitcoin elliptic curve actually looks like. This is what generates public keys from private keys, and is kind of the basis for why Bitcoin is secure. So let's get into the details of why is that the case. What properties does this satisfy? The first property that we'll explore is the idea that if you put any 2 points on this curve and draw a straight line through them, this line will intersect the curve at exactly one more point. Now there's a couple caveats to this rule that we'll go through, but first to just understand why this is the case and why is this an important property. So what we'll do here is we will just create a couple of points. So we can have x1, and I'm actually going to put, instead of just doing x and y here, I'm going to put, make a functional version of this expression. So I'm going to just take the square root of the right side of the equation here, and I'm going to plug in a and b. So what we have is f of x equals square root of x cubed plus 7. And it's important to state that this is only the positive version of the curve. So you see how it's plotted here. It's only above the or the x-axis here for all positive y values. And the reason for this is obviously this curve is symmetrical. So for any x value, there are 2 y values, and we actually lose that when we take the square root like this. But for demonstration purposes here, we will only be using the positive half of the curve. If we wanted to use the negative half, we would have to define this piecewise, and we would have to do both the positive and negative version there. So you see I just flipped it to the bottom half. But anyway, we're going to stick with just the positive version here for example purposes. And I'll now define a point, x1 and f of x1. Okay, so now we have a point, and yeah, we can add a slider as well, that we can move around the positive half of the curve here. And I'll just restrict this to negative 1.9, which is approximately the domain that we have accessible on the positive side. Okay, so let's make one more point actually as well with x2 and add a slider. Okay, so I'm going to set one of these points equal to a fixed value. So let's just keep x1 at x equals 1 here. And our goal is going to be to now develop another intersection line between these so that we can see how this always intersects the elliptic curve at one other point. So we're just going to simply use point slope form for this. First we'll calculate the slope. So m is typically used for the slope, and we have f of x2. So the top half of point slope form is always y2 minus y1, which in our case is we're going to use the function to evaluate, divided by x2 minus x1. Okay, so this is our slope that we will use. And then in point slope form, we have y minus y1 equals m times x minus x1. Oh, we cannot use y1 here. We actually have to use f of x1, as we have been. Okay, so now we have expectedly a line that goes through both of those points. And if we move one of these points around, we'll actually be moving that line as well, since it's all based on that function. Okay, so I'm just going to change our colors up here. So let's keep our original in red. We can do a different color for the points and a different color for the line. Okay, so now let's we can just kind of toggle these points around, and we can visually see that in any place. I actually want this to go minus 1.9 again. So we can visually see that any place we put this second point, if we just take any random pause, you can see there's always going to be 3 points where it intersects the line. In some places it's less obvious, like in that first place. You can see, if you zoom in, you will see exactly 3 places where this intersects. So this is very important for Bitcoin. And actually we are going to define what's called an algebraic group based on this property. So we're not going to go through the details of group theory, but at a high level, what we need is an operator, which we're just going to use addition in this case, and we're going to call this point addition. So if one of these points, or if we're adding 2 of these points together, the result of that addition is the negative y value of the third point. Okay, so p, well, we can call this first point p, second point q, and the resulting value is r. One property that we get to define here when we create our group is that p plus q plus r equals 0, and that p plus q then equals negative r, if you subtract the r over to the other side of the equation. And so what that looks like is if we were to basically just reflect this, what we'll call r, over to the negative side of the x-axis here. That is the result of our point addition. And so this is our first property of this elliptic curve that is used in the foundation of Bitcoin's cryptography. And there are a lot more detail you can go into there. I'm sort of just stating this as a fact, but we could go into, or you could yourself kind of learn about all the mathematical ways you can prove this. But for now, we're just going to state this as a fact. This line will intersect at 3 points, and addition means you draw a line through the points and take the negative version of the third. That's what addition means. We just defined that. Okay? So the next thing we're going to look at is what are these exceptions to this rule? So as I slide these points around, you'll notice there's kind of a special case here. What if x1 equals x2? So they're both at 1 here. You see our line disappeared. And if you think about why it makes sense why it disappeared, because we can't calculate the slope between the same point, right? The slope, and this is sort of why calculus exists in the first place, is as these points get infinitely closer and closer together, we can still calculate the slope, but then as soon as they are equal, we no longer have that point. So what we need to do is differentiate, or take the derivative of our elliptic curve function. Again, we're just going to use the positive version because x at 1 actually has 2 slopes. There's going to be a slope here and down here. We could get both of those if we differentiated both the positive and negative version. But I'm just going to put this in Wolfram alpha here to get that derivative. Okay, so we have the square root of x cubed plus 7. And I think I can just do differentiate. And this is our derivative here. Okay, so I'm just going to add this to our graphing calculator here as a separate function that we're going to call d of x for derivative. Okay, so this is our derivative, and what that means for those not familiar with calculus is this function tells us at any x value what is the slope of the positive version of our elliptic curve. So at x equals 1 here, the slope is something like 1/2. It's not exactly 1/2, but 0.525 there. And that seems about right. The slope here of this line at this point is about 1/2. Okay, so now we are going to try to create this same line that we were before, but at a tangent point, because there's an interesting exception to the point addition rule there that's important before we start building it. So how do we define the line that is tangent to the curve at this point? Well, we know the slope. All we have to do is plug in 1 to our derivative. So I already used m, so we can use s for slope, is d of 1, okay? And we get our 0.5-ish value. That's our slope. And now all we need is, what is the y-intercept that causes a straight line to intersect the elliptic curve at this point, right? So we have y equals s times x plus some constant. We want to know what is this constant so that it perfectly lines up to, and it's going to be approximately 2.3, but we want to calculate it exactly, right? So what is c? So what we can do here is define c, and we just want to set these equations equal. So very simply, square root of x cubed plus 7. If we set it equal to s times x, we can then, or set it equal to s times x plus c, we can subtract over the s times x. So we just have c equals the square root of x cubed plus 7 minus s times x. Okay, but we don't actually want this for all x, we just want this evaluated at 1, right? Because we care about the slope at this 1 point, or the tangent line at this 1 point. Okay, and you see there, we now have our correct value of c. So let me hide the derivative. So if as we infinitely approach the points overlapping, we then get the tangent line, which is defined by in purple here. So this is the first exception to point addition where you actually only have two intersections, right? We have one intersection here at the tangent, and then we have one more down here. And this will always be true. You'll always have these 2 points at any tangent line here. But that kind of throws off our definition of point addition here, where we need 3 different points, and the third point is the result of the addition, or the negative of the third point. So we actually just kind of expand this, this concept of the 2 points kind of coming closer and closer together, and you can theoretically think of this as really there's actually 2 points here and 1 point here. So 2 points at the tangent intersection and 1 point at the non-tangent intersection. And this is what's called point doubling, right? So now we're not adding 2 different points. We are now adding 2 points that are the same. And to double, so instead of P plus Q, we have P plus P, or we're doubling the point P. To do that, all we do is find that other intersection point and then reflect it over the y-axis again, as we normally do in point addition. So this is one of the exceptions that we are going to, when we actually write this code, we're going to have to make an exception for. You know, if these points are the same, we're going to do this doubling method instead of the normal point addition we talked about. And there's one more exception where a straight line that intersects this curve in 2 points will only intersect in those 2 points. And I will turn off these curves here, they're unrelated. So this example is when you have a straight vertical line. So you can imagine if we just had, you know, x equals -1. Well, this line, it intersects at 2 points, and obviously, because it extends to infinity vertically, it's never going to intersect the curve again, right? So we just have these 2 points. So in group theory, there is a concept of an identity. We're not going to go into the details of this, but it's a pretty simple concept. Basically, in normal integer addition, we have the 0, right? Which is completely obvious to somebody that has learned any sort of math, that we have this 0 element, but it's actually, and in the history of mathematics, was not obvious that we would want to include this 0 element. So the fact that 1 plus 0 equals 1. We're going to translate that same concept to this scenario here. And again, we get to define this where we're creating this group so that it satisfies the properties we want. So in this case, if we have P plus what we'll now call is -P, this equals 0. So it actually makes sense sort of algebraically as well. The positive version of the point cancels out the negative version of the point. So that's where we'll leave off with this part of the series. In the next part, we will get into the actual implementation of everything we just talked about in Python, starting with implementing an elliptic curve, second, implementing points on that curve, and then lastly, point addition. So how do we add 2 points and also account for sort of the exceptions or the caveats we talked about today, when points are, in the first case, different from each other, but not inverses. In the second case, how do we add 2 points that are the same in the case of the tangent line, otherwise known as point doubling? And then lastly, how do we add 2 points when they're inverses of each other, giving us that identity or 0 element? We'll also kind of motivate more why this is important for Bitcoin. I didn't really talk about that much in this first episode, but this is really, this point addition is really the crux of why, what defines the relationship between private and public keys in Bitcoin. With any sort of cryptography, we want an easily computable but irreversible relationship between our private and public key. And you'll see in the next part that this point addition is what drives that property of Bitcoin, and how do we actually compute our public key from the private key. So that's where we will pick up in the next part of the series, and I'll see you there.